And that you can even prove that if you take the tensor of two things, which means I take a picture and a picture upside down, picture and picture upside down, that if these two things are equal, then I can extract a diamond from my picture such that this, which makes these two things equal, so they're equal up to a complex phase, with then the phases being normalized. It's amazing that you can prove that, and then basically this is the sort of thing you have to, this is the scalar how it emerges, and the proof is something like this. This is the fastest proof you've ever seen in your life. This is a proof. No, you can't prove faster than this. It's like, I don't know what the time is of like changing the screen, but that's the speed of the proof.
But understanding the proof takes a while.
No. So, just, this was my assumption. This is an assumption. And what you do is you just identify assumption in the picture. So it can't be simpler. So I'm not calculating anything, it's just purely identifying. And this is passing to the complex, so you can say I've got one category of this kind and now I want to make it projective. I can do that. And there is actually a notion of fixed point with respect to this operator which identifies what it means to have a projective category of this kind. And actually it exactly means that if two projectors are equal, you can define I can define projector. Huh? This is projector, two triangles like that. And so the axiom is if projectors are equal, then states are equal. So this is just imposing projectivity. You can do that at this abstract level, no problem. So this, for example, just one thing, this is quantum teleportation, how you describe it in this language. And it's just a trivial derivation. You can find it in the papers which I wrote. So basically this is the preparation of an EPR pair. This is a measurement, a bipartite measurement, and then you have to do some unitary correction. So you see, we saw how all these co-states arise by just taking the adjoint of the bell state and the morphism. And then if you pull the rope, these two annihilate each other and you've got teleportation. So that's how in this language you derive teleportation. This is the usual description. And you can actually, this would be the categorical description of the same thing. So you can actually write down a really concise abstract formula which represents this picture. This is like the syntactic representation of this picture in category theory terms.
So what is it physically?
What?
What is it physically?
This is teleportation.
Yeah, but I heard Bezel talk about it and I understood.
Ah, you want me to explain? Quantum teleportation protocol, it means you've got a state of a system here, and you want to communicate it to the other side. So and you don't want to sort of send the state physically. So what you do is you've got a state here, you have a bell state sitting there, and then you do a bipartite measurement here, and then you communicate the outcome of the measurement to some other guy who does a unitary correction, and then it turns out that you find the state of the system at the other side.
That's exactly what I told you. Right?
And the only the thing is, state of the system is continuous data, and the only thing you communicate is actually two classical bits, which is the measurement outcome. Now, I have to say, this is ugly, you see, I have to write I here. And this is not nice in my picture calculus. That I have to write I, and then say I communicate. So actually the last part is intended that we can get rid of these I's, and can actually implement abstractly the quantum measurement stuff. That's new stuff you never heard about, by the way. So this is the last thing you heard from me, I guess. So anyway, this is how teleportation usually looks, and it took like 6 eminent scholars about 60 years after the start of quantum mechanics to invent this. Hey, so I'm going to skip that. And I'm just going to screw to this, but because that's where actually I think most of the physics or the physical output of this setting would come in, and that's the fact that so far I haven't been talking about measurement. And it turns out that this setting is enough to actually consider measurements without addition, and you don't need additional structures. In the papers I've sent you, we use this byproduct stuff. You remember that? But you asked me about it.
Yeah.
So you don't need all that stuff.
Okay.
You don't need all that stuff. So here is the game. So I said already, this is the type of quantum measurement. From quantum data to classical data, quantum data. Yeah. Now, what this requires is to be able to distinguish classical from quantum. It's a big question of physics. What's the difference between classical and quantum? And if I want this thing to work, if I want this stuff to work, then I should, within my setting, which is very weak, which is very abstract, be able to distinguish classical from quantum in one way or another. And hopefully get something out of that and some representation theory that I actually get measurement theory out of that in the Hilbert space case. Now, that's the following thing, which is the thing which I'm surprised, it's amazingly surprising that it works, but so how do I define classicality? And this is where, and we won't need an observer. We won't need the notion of observer, that's the funny part. So I can define classicality in this setting without having to rely on an observer or saying whether the observer is part of the quantum mechanical world or not. And that's how I do it. So this is my classical data type. What can I do with classical data? I can copy it. In the classical world you can copy data. So there is some operation from x to x times for x. In the classical world that exists. So I'm assuming that a classical data type comes together with an operation of copying and with an operation of deleting. It's very innocent. That's what I'm going to assume. I define a classical data type as a triple, copying, deleting. There's no observer there. There's no observer. Just the ability to copy and delete the data. And so there is a definition there. And now, like, everybody knows what a monoid is. Yes? A monoid is a semi-ring with a unit. Or a group without inverses, if you want. So that's a monoid. What is a monoid? A monoid is you've got some set x, and you've got a multiplication from x times x into x, and you've got a unit. Yeah? So you pick out some element. Typically in set theory, this is a singleton set.
I mean, the natural numbers form an example.
What?
The natural numbers form an
Yes,
example.
yes. So, but it's crucial is you've got an operation from 2 to 1, and an operation from 0 to 1. Unit and multiplication. Now, in category theory you can do nice things like reversing the arrows. This is comonoid. And this concretely it's hard to think about this, but abstractly this is just the easiest thing. Now, and this basically means just I can copy and I can delete. Now, this is associativity. Right? I copy once and then I copy that. If you read from top to bottom, you see I multiply first these two and then I multiply it with the third one. Here it's I first multiply the second and the third and then I multiply it with the first one. That's associativity. This is co-associativity. This would be, I've got a unit. I multiply something with something and you always get the same thing. This is co-unit. I delete, and this means I delete and then I erase one. Should give me the identity. This means it doesn't matter in which order. If I copy the first or the second outcome, doesn't matter. So this is called comonoid. So and then except for comonoid, we ask this comonoid to be commutative because copying doesn't matter which of the two copies you assume. And then we need some additional assumption, which again can be given some interpretation in terms of this adjoint stuff. But I'm not going to go through it. And basically you can then derive from this that this copying operation and this deleting operation don't see complex numbers. In the classical world you don't have complex phases. And this will mean that the lower star of this copying and this deleting is just trivial. This is something which, so I'm not writing down the exact definition. Now, basically, now I'm going to do some basically there is a result which says that internal commutative comonoid structures over Xi in 1-to-1 corresponds with commutative comonad structures. Now, who knows what a comonad is here? Or a monad? Monad. If you know monad, you know comonad. It's just monad upside down. But,